Section 8.6 is integration by tables and other techniques. What does integration by tables mean? Matrices. No matrices. I might give you the integral of 1 over x squared times the square root of x squared minus 4. How would you integrate that?
I feel like that's a trig. Yeah.
I feel like that's a trig substitution also. And what is telling you that that looks like a trig substitution? You've got a square root, and inside that you have a
U squared minus a squared.
You have a u squared minus a squared form. That's a trig substitution. But that's not what you're going to do in this section. What you're going to do in this section, you're going to look in the integration tables. This is what we mean when we say integration by tables. So you're going to look for one that fits that pattern. Let's see. Do you see one yet? 17? No, because we need x squared minus something. That one's not quite right. I don't think this is. There's more of them. You see one yet?
Yeah.
Yeah, which one?
35.
35. So you look in the back of the book, and you find the one that matches.
So we get the books on test, right? Yeah.
No, we won't do much integration by tables on the test. But in reality, this is what people do a lot of times. This is what people really did before they had Wolfram Alpha. You guys don't do integration by tables anymore. You do integration by Wolfram Alpha. All right, so our answer would be, first off, we have to notice that we have u squared minus a squared, so we're in the minus form. So the answer is, what this tells you is if you have the minus here, then in your answer you have the plus. So it's going to be square root of u squared minus a squared, so that's x squared minus 4 divided by a squared times x, that's 4x plus c. Is that a little bit easier than integrating by parts? Yeah. So what did somebody do? Somebody took this, put it in this form, and integrated it using trig substitution for you. And they came up with a pattern. And so now, in reality is, we use the pattern. All right, let's try another one. That was so much fun. Find the right page again. Not that page. Not that page, but we're getting close. All right, how about, I don't know, the integral. Somebody pick one. Which one do you like?
35.
35. The integral of x over the square root of x to the 4th minus 6x squared plus 5 dx. Okay, so I flip back to my big chart of integrals. Let's see, it can't be any of those, right? Because it's going to have something with a square root in it. Look like any of those? No, I don't think so. Those all have some square roots in them. Those don't look right, do they? Looking. See the what? Right one yet? No? All right. Next page.
I've never seen that form. I wouldn't know how to do it.
I looked at all 100 of them. I didn't see the right one. So what do? Simplify it. All right. What do you mean by simplify it?
Try to get it into a form of one of those things.
Try to get in the form of one of those things. All right. And notice what these forms all have. These forms typically have a square root, but they have x squared plus or minus a squared. We've got something with 3 terms here. So what do you think we're going to have to do?
Break it up.
Maybe break it up. That's not. I don't think that's the right way to go.
The square.
I think we need to complete the square to make it be in the form of something squared plus or minus something else. Before we complete the square, though, I also noticed that this one has x to the 4th in it, and all these integration forms only have x squared in them, or u squared in them. How am I going to fix that? So, I think the first thing we're going to do is we're going to do a u substitution, u equals x squared. So sometimes you're given a problem and it doesn't immediately fit into the form. Sometimes you do have to do some work still. So if u is x squared, du is 2x dx. So this becomes 1/2 integral 1 over square root of u to the 4th, u squared minus 6u plus 5 du. So I think that's the first thing we have to do on that one, is do a u substitution. And then I think the next thing we need to do is complete the square, because there's none of the forms that have 3 terms. They only have 2. So I'm going to come off to the side here. U squared minus 6u plus 5. And that's u squared minus 6u plus, what number do I need to add? 9. So plus 5, and then subtract a 9 to balance it. That factors as u minus 3 squared minus 4. All right, so now I've got 1/2 integral 1 over the square root of u minus 3 squared minus 4. When I go to look at my integration chart now, what am I looking for?
U squared minus a squared.
I'm looking for u squared minus a squared with a square root over it. Okay. Hey, I found one. U squared minus a squared with a square root over it. Except we're not going to use u. We're actually going to have u minus 3 wherever we see the letter u. Okay, so our answer becomes 1/2 ln of u for us is actually u minus 3 plus the square root of u squared minus a squared. So that's u minus 3 squared minus a squared plus c. Not quite done. My original problem started with x's, so my answer should end with x's. Wherever I say u, I'm not going to write u, I'm going to write x squared. So final answer, 1/2 ln x squared minus 3 plus the square root of x squared minus 3 squared minus 4 plus c. Questions on that?
So will you be given this table for the test? Unfortunately, you're going to have to shrink down 100.
Neither. You won't need the table.
Okay.
You'll do things like integration by parts, integration by trig sub, so on and so forth.
What page are those on? Yeah.
The table,
Yeah.
it starts, it's appendix B, which is page A3. Way in the back here. Integration table, see, it's appendix B, there it is. Now, I don't want you to think that your book gives you 100 integration forms. Is that all of them? No. In fact, I have this book here. This is the CRC Standard Mathematical Tables and Formula. And if you look in here,
So does it have it like, the problem just did, does it have like in the form there was? Something like that?
I don't know, it's got all sorts of amazing stuff. So it starts right with the integral of a dx is ax plus c. They didn't put the plus c on all these. And then you got your basic integration rules, you got your rule for log, and it goes on and on and on and on and on and on. Exponential forms, hyperbolic forms. Oops, skipped a page, that's okay. Eventually, oops, not too far. Eventually it starts giving you formulas for definite integrals too, like the integral from 0 to infinity of x to the n minus 1 e to the negative x, is whatever the world that is.
Yeah, what is that symbol?
Yeah, the upside down U there.
Which upside down U, this one?
Yeah.
That's a symbol for multiply. So that's a multiply m equals 1 to infinity of that stuff. Multiply it all together. This function here is known as the gamma function. So it's got definite integral 0 to infinity, 0 to 1, so on and so forth. So this book has a mere 724 integration formulas. Is that all of them? I highly doubt it, because this book, I looked this morning, it has a copyright of 1991, which is when I was given this book. I'm sure there have been more developed since then. Lots of them. All right, so that starts to give you an idea of how Wolfram Alpha is working. A lot of these formulas are programmed in, and it's just looking up the formula, plugging in the numbers, and giving you the answer. So,
Imagine that C++ program.
yeah, imagine that C++ program. That'd be a good one. All right, the one thing that is new in this section is integrating fractions involving trig functions. And you're going to use this substitution. Substitution for rational functions of sine and cosine. U is going to be sine x over 1 plus cosine x, which turns out to be tangent of x over 2. And once you have that U substitution, cosine x is 1 minus x squared over 1 plus, or cosine x is 1 minus u squared over 1 plus u squared. Sine x is 2u over 1 plus u squared. And dx turns out to be 2 du over 1 plus u squared. So you use those substitutions for rational functions of sine and cosine. What are rational functions of sine and cosine?
Roots.
Rational does not mean root. Well, we don't deal with any imaginary in this class, so it's definitely not imaginary.
Like you can put in your fraction.
Yeah, what does the word rational mean? In a math class, rational means fraction. Rational means ratio. So what you're going to be looking at are problems like this, where you have fractions. Your fractions involve sines and cosines. So let's work through one of those. Which one do you like? 59. Why do you like 59? 59 and 54 were the two good ones. Those are the ones you were going to pick if you had a choice. 59 has the integral sine square root of theta divided by square root of theta d theta. How would you integrate that? U is square root of theta, and then du is 1/2 theta to the minus 1/2 d theta. But what's theta to the minus 1/2? 1 over square root of theta d theta. This is not a Calc 2 problem. This is a Calc 1 problem. That's why I said if you could pick one, that's the one you want to pick. This is an easy one. So I need a 1/2 in here, but then I need to balance that with a 2. So this ends up as 2 integral sine u du. What's the integral of sine u? Negative cosine u. So this is negative 2 cosine square root of theta plus c. So that one didn't need any fancy substitution. That was a standard, straightforward u substitution problem. If you had to pick another one, the other one you would pick would be which one?
54.
Why do you like 54?
Because 1 plus cosine squared, you can multiply and you can cross out.
So you want to sign.
I don't think so. 1 minus cosine squared would give me sine squared.
Just throw us
You can make u just be cosine. The derivative of cosine will give you a sine, and you end up with a 1 over 1 plus u squared form, which is, that's an arctan. So again, this one's almost a u substitution. So let's pick one that's not. Let's do number 53. 53 would be the integral of 1 over 2 minus 3 sine theta d theta. Notice with this one, you can't do a standard u substitution. You really like to let u be sine, but if u is sine, what happens? I need a cosine, and I don't have one up here. Okay? So a problem like this, that's where you're going to skip back, and you're going to use these substitutions. So instead of sine theta, I'm going to have 2u over 1 plus u squared. So this integral is going to become the integral of 1 over 2 minus 3 times, instead of sine theta, I use 2u over 1 plus u squared. And then instead of d theta, I use 2 du over 1 plus u squared. 2 du over 1 plus u squared. All right, so when your standard u substitution doesn't work for sines and cosines, that's what you do. Now what?
Distribute the 1 plus u squared.
Distribute the 1 plus u squared. That's a minus right there, and that one's a times. All right, so we're going to have integral of 2 over, when I distribute, I have 2 plus 2u squared minus, when I take this 1 plus u squared and multiply it by this, I'm just left with
6u.
6u. du. All right, I'm going to rewrite that. That's integral. I'm going to do two things. First off, I notice that everything can be divided by 2. So I'm going to divide everything by 2, and then I'm going to put things in order. That's 1 over u squared minus 3u plus 1 du. All right, so there's the idea behind that substitution. We do that substitution to get rid of the sine and cosine, and we end up with a rational function. We know how to integrate rational functions, for the most part. How do you integrate that? By complete the square. Because then you'll get into something we know. There's something you should try before you jump to complete the square, but it doesn't work for this problem. You should try to factor the bottom. Why would that help if you could factor the bottom? No. Break it apart using what? Not integration by parts. Partial fractions. So if it turned out that this bottom factored, we could then use partial fractions, which I prefer over completing the square. That's my choice. Completing the square will always work and always give you an answer. But if you can factor, I would prefer partial fractions. Unfortunately, that bottom does not factor. So I agree with you. I do need to complete the square. All right, so I'm going to have u squared minus 3u plus 1. That's going to be u squared minus 3u plus, what's the magic number?
1.5 squared.
1.5 squared, which is 9/4. It's better to leave it as a fraction. It's 3 divided by 2, and then you square it. So 9/4. Plus 1 minus the 9/4. Okay. Here's u squared minus 3u plus 9/4 factors as u minus something squared. What's the something? 3/2, because 3/2 times 3/2 will give you that 9/4. Minus 1 minus 9/4. Negative 5/4. So u minus 3/2 squared minus 5/4. All right, so this is the integral of 1 over u minus 3/2 squared minus 5/4 du. Does that fit one of our magic formulas?
U squared minus a squared.
It's in the form of u squared minus a squared. So what's that? It's not sine. Sine would have a square root there. What's that? Arc cotangent, very close. Arc cotangent would have a plus in the middle. Arctan would also have a plus in the middle. Arc hyperbolic tangent. That's awful. But remember what we did with that we didn't write it in terms of inverse hyperbolic tangent. We wrote it in terms of its ln form. It's 1 over 2a. So that's 1 over 2 square root of 5/4 ln I can never remember if it's u plus a over u minus a, or if it's u minus a over u plus a. It's one or the other, though.
U plus a.
U plus a. So it's going to be u minus 3/2 plus square root of 5/4 over u minus 3/2 minus square root of 5/4 plus c. And then you got to look back here. When you make this substitution, u is tangent of x over 2, so that's how you get your x's back in. Final answer. Not one of the nicest answers I've ever seen. 1 over 2 square root of 5/4 ln tangent of x over 2 minus 3/2 plus the square root of 5/4 divided by tangent of x over 2 minus 3/2 minus square root of 5/4 plus c. Questions on that?
And the easier way to do this is
Doing it by hand, the only easier way to do it is flip to the back of the book. Look to see if there's one that fits the pattern. Let's see, things involving sine and cosine. It almost works, except we had numbers in front. So I don't know what you would do with our numbers that we had. Have to find a better formula, I guess. I don't see one in here that would work. There's probably one in the other book that would work, though. Be my guess. Yes, Nick.
Why did we do that sub for tan x over 2?
That's the whole technique here. The whole technique is, find the right page again. The u substitution, you're letting u be tangent of x over 2. And when you do that, that's what cosine turns out to be, that's what sine turns out to be, and that's what dx turns out to be. So when you get all done, and you've got your answer that involves your u, you're going to get rid of the u and get your x's back in by using u equals tangent of x over 2. So in the beginning, you substitute for the sine, the cosine, and the dx. And then at the end, you get rid of the u by plugging in tangent of x over 2. Other questions?